right, we're going to look at the proof. All right, so here's the question. We're looking at the L2 induced norm. That is the induced norm associated with signals of finite energy. And we've said it's equal to this. All right, so how do we prove that? So this is really a sketch of the proof. The proof is actually much more involved in this, but this is most of the proof. So if I look at it in the frequency domain, Z of S is equal to H of S times W of S. And gamma then, we're going to just define it to be this quantity. Okay, we're going to come back later and show that this is actually the H infinity norm. All right, so notice that in this process, by defining it this, we're actually, gamma here is the supremum over all omega of this, which means if we were to use this as a formula for calculating the H infinity norm, this doesn't do very well for us either. That is, I have to pick a value of omega, calculate this quantity, pick another value of omega, and so forth. In general, it's not that easy to get this expression, for example, as a function of omega. Take the derivative, set it equal to 0, and all that kind of stuff. So this basically requires also an iterative process, trying various values of omega. Well, so in order to show that the we need to first of all, in order to show that this gamma is in fact the H infinity norm or the L2 induced norm, I need to show this inequality in terms of L2 functions, right? For W finite energy, if W is any finite energy signal, I need to show that Z, the output, is less than or equal to gamma squared times this value. That is, I need to show that gamma is an upper bound on this inequality. So remember, the L2 induced norm is equal to the largest ratio of this over this. Okay, the largest ratio. And so I need to show that gamma is greater than or equal to that largest ratio. So it turns out, so first of all, I need to show that gamma is an upper bound. Second of all, I need to, if I can, I need to show that there is an actual input such that equality is achieved. Okay, so and here is asymptotically achieved. So we're actually going to do this. The formal proof involves using convergent sequences of functions and so forth. All right, so we have this relationship, and by Parseval's theorem or Plancherel's theorem, depending on who you're talking to, some people prefer to just go ahead and call it Plancherel's theorem. The energy in the frequency domain is equal to the energy in the time domain. Okay, so actually Parseval's is a special case of Plancherel. So in the time domain, the energy squared is equal to 1 over 2 pi, is equal to the integral from 0 to infinity of z transpose z dt. But using Parseval's theorem, we can do that in omega, so which is 1 over 2 pi times the integral from minus infinity to infinity, z adjoint of j omega, z of j omega. So notice z adjoint of j omega is the complex conjugate transpose. That's actually equal to the transpose of z times with evaluating z at, instead of j omega, minus j omega, or the conjugate of this. So, but z is given by this expression, and so I plug this in here and I get this. So this is the expression I have. So this is equal by Parseval's theorem. So I have this quantity. That quantity is less than or equal to this quantity, where now instead of looking at the infinity norm, rather than looking at this quantity, we're going to use the maximum over all omega. Rather than using this quantity, we're going to use the largest singular value of that. So that is, this quantity is less than or equal to W adjoint W multiplied by the largest singular value. So that's where this inequality comes from. So because this largest singular value is a scalar, I can take it out from the middle of this, and this is what I have. And now this quantity is less than or equal so I'm evaluating this from from omega from minus infinity to infinity, and now I can actually take this quantity outside of the integral by looking only at the maximum over all frequencies. So in general, this is a function of frequency, and I can take that outside if I look at only the maximum, and then I get this another inequality. This quantity here is actually the 2 norm. That's the energy in the frequency domain for W. Okay, and so we see that this is less than or equal to this quantity times this. And so we have shown that gamma is in fact an upper bound. So that's gamma, and it is an upper bound on the output energy with respect to the input energy. So we've shown that it's an upper bound. Now we need to find a signal W that closely approximates this. That this gives equality here. So we can do this using the so-called resonant frequency. So the resonant frequency is the frequency at which the system has the largest response. Okay, so the largest singular value of the transfer function of omega. We look at the largest value over all omega, and we choose. So arg means I'm going to use the omega that does this. Okay, it's the omega at which the supremum occurs. Now I'm going to apply this function W to the system. So this is a complex sinusoidal input. So, and we're only going to apply this between 0 and time cap t. Okay, so it's a finite interval. So if you have a sinusoid and it oscillates in a finite time period, that signal is finite energy. If you let that thing go all the way to infinity, then it's infinite energy. But if you just chop it off at some time capital T, it's finite energy. And in fact, the fact that we've divided this by T gives us energy that's equal to 1. Okay, gives us energy that's equal to 1. So this signal is chosen to give us energy equal to 1. Now the output of a stable linear system to a input sinusoid is basically a sinusoid of different magnitude and phase. So this is what we're looking at. And in this case, we're actually looking at it in the scalar case. So in the scalar case, this is the response. Our output, when you apply a sinusoid to a linear system, the output is a sinusoid, different magnitude, different phase. So that's the concept of the Bode plot. The magnitude is the magnitude of the transfer function evaluated at that frequency. The phase is the phase of the transfer function evaluated at that frequency. So we talked about the signal having finite energy. That is, we start at time 0, we go to time capital T, and as long as we have a fixed capital T, that signal is finite. So now what we're going to do is we're going to let that T slide. Okay, we're going to let that T slide. So for large T, the transient portion is negligible, and we have basically that Z, the magnitude of Z is equal to the magnitude of the transfer function evaluated at the resonant frequency times the norm, and this is what we get as T goes to infinity. And so we actually have that the 2 norm is arbitrarily close. So remember, this is actually for a scalar system. This is actually the largest magnitude of the transfer function, right? The resonant frequency. So we then take the limit as T goes to infinity. Actually, we don't have to actually go all the way to infinity. We can stop at any point and get arbitrarily close, these being arbitrarily close to one another. And that's really what we need to prove this. And that's why I say it's kind of a sketch of the proof. If you wanted to be rigorous and actually do it mathematically, then you would say we'd choose an epsilon greater than 0, small, and we need to show that we can come within epsilon. For a finite energy signal, we can come within epsilon of having Z, the 2 norm, equal to this within epsilon. That is, the difference between these two signals is less than epsilon. So it's arbitrarily close. So that is actually the proof. Boom. And it's important to recognize that the question of how would we actually compute the H infinity norm is important. So in the lecture slides, we've gone through and shown how to compute the H infinity norm. But this is the proof that that finite energy signals have as their induced norm the H infinity norm.